We're going to make the jump from dealing with um, a single population mean using the z distribution to a single population mean using the student t distribution. What the z um, table was allowing for us, the normal distribution was allowing for us, um, was through the use of the central limit theorem to make the argument that if our sample size was greater than or equal to 30 and the um, population standard deviation was known, we could determine the 90, 95th, 99th percent confidence intervals. But what we find out in actual practice is that it is very rare to know the population standard deviation. Okay, so we're going to be trying to estimate a confidence interval for the population mean mu, but now we're not going to know the population standard deviation. So what happens is that we can replace the standard deviation, which is sigma of the population, with the standard deviation of a sample. Okay, says the t distribution, or what we call the student's t distribution, arises when estimating the mean of a normally distributed population when the sample size is small and the standard deviation is unknown. Okay, or the population standard deviation is unknown, and we must estimate it from our data. Okay, so like I was saying, the central limit theorem allows for statisticians to use the normal standard distribution when sample sizes are big enough, but the scenarios that we're going to look through right here, the sample is not going to be 30 or larger. It's going to be smaller than that, and we're not going to know the population standard deviation. Okay, so the central limit theorem, I'm not saying that when n is less than 30 that something, the central limit theorem will not produce normality. It just doesn't guarantee it. Okay, so a little history about why is this called the student t distribution. The guy that discovered it or realized it was by the name of William Gossett, and he was a statistician employed by the Guinness Brewing Company. And he was looking at like yields of barley and experiments that he could do to maximize the yields. Um, and Guinness would not allow him to publish his work under his name, so he used a pen name student. So that's why it's called student's t distribution. Um, It says when the population standard deviation is not known, the sample standard deviation can be used in place of the population standard deviation for confidence intervals. Okay, so in the confidence intervals that we've been dealing with, where we said x bar, all right, plus or minus my error, okay, my standard error, which we were finding that e was equal to z sub alpha over 2 times sigma over radical n. Okay? And here's the issue. That number right there is rarely known. Okay? That's the population standard deviation. We don't usually know that. So that's why we start talking about this t distribution, because it is now going to allow us to determine confidence intervals, but using a different distribution. All right, so here are some characteristics of the t distribution. Okay, one is that it is bell-shaped. Okay, much like the normal distribution is. Okay, it's symmetric about the mean, much like the normal distribution is. The mean, median, and mode are equal to 0 and located at the center of the distribution, just like the normal distribution. Okay, the curve never touches the x-axis. The x-axis plays an asymptote, or plays the role of an asymptote. Same thing that a normal distribution plays. Okay, but there are some things that are different. Okay, this is the t distribution differs from the standard normal distribution in the following ways. The variance is greater than 1. The t distribution is actually a family of curves based on the concept of degrees of freedom. My hope is that you've watched the videos that I asked you to watch previously over 8.1 to understand what I talk about degrees of freedom. Okay? Without those videos, degrees of freedom might not make much sense to you. Degrees of freedom in regards to the t-distribution are based on the sample size. It says as the sample size increases, the t-distribution approaches the standard normal distribution. Okay? It says many statistical distributions use degrees of freedom and are calculated in different ways for different statistical tests. The degrees of freedom are the number of values that are free to vary after a sample statistic has been computed, and they tell the researcher which specific curve to use when a distribution consists of a family of curves. Um, Again, that's a very brief discussion about degrees of freedom. Much more detailed explanation discussion should have been analyzed previously through some of those videos. All right, so I just want to take a peek here at what the normal versus the t-distribution looks like. Okay, so I spent some time making this GeoGebra to hopefully get you to see the difference between the two. Okay, so this allows me to do is basically puts in two distributions here. So I'm going to show you the normal distribution, which we're used to. Okay, and then show you. So this is the normal distribution, and if I want to go from, let's say, negative 1.96 to, let's say, 1.96. Okay, and I'll show the area underneath there. And that's the 95% confidence interval. Okay, so that's just doing some calculus behind the scene with the intervals gives us that area of 95%, or 0.95. And that should make sense from the z-scores that we were realizing for the alpha over 2 for being 95%. Okay, so if we looked at the, so this is what, 0.025% right here. So if we look at 0.9750 in the t table, sorry, the z table, we would see 1.96 being the z-score that attaches to that. And then obviously, since we're symmetric, we have a negative 1.96 as well. So that's something we've known. Okay. Now, if I look at what we refer to as the t distribution, okay, here's a t distribution. And now the t distribution is using what we refer to as degrees of freedom. And we'll find out that the degrees of freedom are going to be one less than the sample size. Okay? So what we find out is that obviously going off of the characteristics that were being provided earlier is, this is still symmetric, centered at 0 for the mean, median, and mode. X-axis is an asymptote. And the area underneath is still going to be probability. Okay, it's still going to sum to 1. The comparison now is this. So usually what we argue is that when the degrees of freedom are below 30, that the normal distribution and the t distribution, they are similar, but the normal distribution, is got a higher peak, or the t distribution's got a lower peak, and the t distribution we say has fatter tails. Okay, if I show you, let's just go from a positive 1.96 to, I think, going to like 3 or 4 would be fine for a normal distribution. But I'm going to go up to, I think I've got this set up to allow me to go to 500 maybe. So next value out to 500. And if I show you the area underneath the normal curve, there's that 0.025 that we know as that right tail for z sub alpha over 2. Okay. Now, if we look at the area under the t distribution, we get 0.15. Okay, so that 0.15 is a much greater area than the 0.25 or 0.025. Okay, so what we say is that for a for a t distribution, the tails are fatter than that of a normal distribution. Okay, but what happens as we increase the degrees of freedom, we start to see those tails get a little bit less fat, and we see the peak of this distribution start to approximate the same height as the normal. And that's what the degree of freedom right now, 15, 16, we get up here, get up to 30. We're very, very close to being the same distribution. And if I go up to 60, it's even closer. Okay? So that idea allows us to use a t-distribution to develop some confidence intervals. Okay? What is, I think, useful to realize is if we go from, so let's just show the normal distribution over here on the left-hand side. And again, I want to show that area of 1.96. Okay? If we look at the t-distribution on the right-hand side and show the area from 1.96. So now you see with what we'd be looking at here, because the degree of freedom is 1, we'd be looking at a sample size of 2. So you're taking 2 objects from a population, okay? And we find out that from 1.96, basically we call this a t-score from 1.96 to the right, so this right tail has an area of 0.146, or 14% of the area underneath this curve is to the right of 1.96, where we're seeing over here 2.5% of the area is underneath the curve to the right of 1.96. And that's with the degrees of freedom 1 or a sample size of 2. So if I increase my sample size to 3, you see what happens to that 1.4 number, or 0.14 number. It decreases. Okay? So as this thing starts to increase, okay, what we start to find out is the more and more the sample size starts to increase. The greater the sample size, the better the approximation that we have for the t-distribution to model that of the normal distribution. Okay, so those are some relationships that are very useful in understanding as we progress through the t-distribution, or sometimes obviously called the student's distribution. We've messed around a little bit with GeoGebra, Desmos. I don't know. I'll have to play around with it a little bit. The command in Desmos, if there is one for a t-distribution. Same thing with Excel. I haven't used those too much. I just, in using t-distributions in the past, it's always been using a table and formulas. Okay, so I'll look into some technology in the next couple days and see if I can send that on to you. But if we look at a probability calculator here in GeoGebra, it does have something to do. Now I've never messed with it here, but it does have something to do with the t-distribution. So if I click on that link right there, that box, I get all these different distributions, and you don't see t, but you see student distribution. Okay, so and then you see the degrees of freedom and all that kind of stuff that are working here. And my assumption is that you're gonna utilize these boxes and the probabilities here the same as you would when we were messing around with the normal distribution. All right, but the purpose of this distribution is to allow us to, like I said, create confidence intervals and eventually deal with hypothesis testing. That's what basically the z-score and the t-scores here are going to allow us to do, is to do something called hypothesis testing, which we'll get into here pretty soon. And then this is just a situation when we're going to use this formula when we're trying to find a specific confidence interval for a mean when the standard deviation of the population is not known and you're taking a sample less than 30. Okay. So notation is very similar to what it was for the Z table and the confidence interval with when the standard deviation was known. You're going to take your x bar, which is the sample mean, subtract from it t sub alpha over 2, okay, and that t sub alpha over 2 is very similar to z sub alpha over 2. Sometimes, and you see it in my explanation here, sometimes you'll see that as t sub c, where then they say c is your critical level, your confidence level of 95, 99, whatever. S is going to be your sample standard deviation. N is your sample size. Okay. This thing here, like I said, is going to be found from a chart. And again, it has to do, the charts, remember, are going to give us these areas. Okay. So these charts that we're dealing with, this one's going to be constructed a little bit differently because that area, when I have a sample size, right now I'd have a sample size of 61. That's a little bit different than having a sample size of 60, which is a little bit different than having a sample size of like 34. So the chart is still referencing areas that we get through intervals from calculus, but it's constructed a little bit differently because it's now a family of curves instead of just this one normal curve. So I'll teach you how to use that. It's not that difficult. Our notation for degrees of freedom is always d dot f dot, and in this case, the way we find degrees of freedom is n minus 1. Remember, n was your sample size. Okay. So the values for finding t sub alpha over 2, like I said, t sub c some cases. So the top row labeled confidence, I'm going to show you a confidence table here in a moment. It says the top rows labeled confidence intervals is used to get these values. The two other rows that are labeled left tail, right tail, you're not going to use those in this context. So the t distribution and the t table that we're going to use is going to be, again, used in hypothesis testing, and that's when we'll talk about these other two rows. But for right now, just finding the confidence intervals, we're going to use the top row, and we are going to look at something in this situation. It says, like I said, t sub alpha over 2 can sometimes be written as t sub c. So they might say find a confidence interval for a 95% confidence level, and you'll know you're using the t distribution. So they'll say t sub alpha would be 5%, because that's the 1 minus your confidence level is your alpha, or they will write it this way: confidence interval of 0.95. Okay, you kind of see it both ways. But what this means to us, and this is what their table is going to look at. Now, you could do a quick Google search and find different structures of t distributions. You just have to pay attention to how they're written. They're all kind of similar. This is the one that I prefer. And I've posted this on Schoology. I suggest that you put this on your desktop or print it off or whatever may be the case. But what I'm going to ask you to do here is let's find the 95th percent or the 95th percent confidence level for, let's say, a sample size of n being, let's say n is 15. Okay, so what we're going to do is we're going to look at this top row. That's the confidence intervals. That's the top row I was talking about. we want the 95th percentile. Okay? So, like I said, these two, one tail, two tail, that doesn't matter to us right now. Those are some tests that we'll do later. What we're going to do is it's very similar to what we did with the Z table. We're going to pick our confidence level, and we're going to pick our degrees of freedom. Okay, so I said 15 was our sample size. So we're going to go 15 minus 1 to determine our degrees of freedom. So that gives us, that's basically telling us now that we're going to be looking at this image, okay, in contrast to any one of these other curves that we could create using the t distribution. Okay, so obviously we got a family of curves. If n is 15, the degrees of freedom tells me that we're use this chart here. Okay, so if I want the 95%, and I'm using a degree of freedom of 14, I'm going to find the 14, go straight across, and I'm going to pluck off this 2.145. 2.145. Okay, so 2.145, let me write that down. And remember what we were talking about. We had n to be 15, so the degrees of freedom was n minus 1, or 15 minus 1, so 14. Can I talk about what this means? If we've got our t distribution here, okay, so it's a t distribution, and then if you're interested in that curve, just much like the normal distribution, it's got a formula. It's pretty nasty, much like the normal distribution formula was. So here is a version of the let's actually this one. So this is a version of the standard normal distribution. Okay, with sigma being 1. Here is the formula for finding the t distribution. Okay, pretty nasty looking thing. But if I just put the curve there and don't put that it's a t distribution, you might think this is a normal distribution. Okay, but basically what we're doing here with this 2.145 is saying on this curve, if I go out to a t-score of 2.145 and here a t-score of negative 2.145, we should then in between have 95% of our area. So let's see if that is confirmed here on one of these. So I don't need both of them. Let's get rid of that one. So I'm going to show the area under the t distribution. I want my interval to start at negative 2.145, and I want it to go up to a positive 2.145. And so that gives me 0.722, and that doesn't match up to 95%, but look at my degree of freedom right now. I have a degree of freedom of 1. So let's get that degree of freedom up to 14, and there you see that it grows to an area of 95%. Okay, but if it was a lower degree of freedom, it's a lesser area, lesser confidence interval. Okay, so that same 2.145 number, when I have a sample size of 3, essentially, I can't be as confident if my sample as confident as I am with a sample size that's larger. Remember, we have the idea that the larger the sample size, the less the variability in regards to our mean. Okay, so that's essentially how we garner those values that we're going to use inside this formula. Okay, so all I want to do right now for the rest of this video is to find these remaining confidence intervals. Okay, or confidence values, these t-scores essentially. So 50% for n equaling 5. So 50%, and actually I must have been looking at, I think what I was doing, so this t distribution comes from a different textbook than our textbook. I think our textbook actually had a 50% in it. And that's another varying contrast. So obviously the confidence intervals that we use the most are 90, 95, and 99. Some tables are going to, for the t distribution, are going to incorporate obviously those three, but they'll also incorporate others. This one incorporates 80 and 98. So let's go ahead and change this one to 98. So we're on 98% for n equals 5. So I'm going to go 98 column, degree of freedom. So if n is 5, degree of freedom is 1 less than that. So go to 4, see where they intersect. So I'd be picking off that number right there, 3.747. And that's going to be my t, what we would say, that's going to be my t of 0.98. Okay, 98%. And it's 3.747. And that's obviously the right tail, or the identifier for where the right tail starts. If I want the opposite of that, we would just do this. And that's obviously, that's going to give me, if that's my mean there, this is the t of 0.098, then the symmetry is going to tell me that that's opposite of t of 0.98. Put my decimal point in the wrong spot there. And what basically we can argue is that this is symmetric. So once you find that one to the right, you automatically know the one to the left. So this would be, this 3.747 number would actually be the one that goes there in our confidence interval, and the negative one will go there. Okay, but if we ignore this minus sign here, well, if we put negative 3.747 here with that minus sign, it turned into a positive, and that'd be a problem. So because the formula is already written out with a minus sign here, you can just put 3.747 in both those. This one will be a minus, and this will be a positive. If we go 80% for n equals 14, so 80%, first column here, n equals 14, so degrees of freedom will be 13, and we'd be looking for a 1.35. And then 99 with n being 25, so that's my last column, n being 25, so degrees of freedom would be 24. We're going to pick off that number, 2.797. And that's how we find our, ultimately we're going to call z-scores. Here it says I identify the z-score, z sub alpha over 2 for a 99% confidence level. Okay. My hope is that you guys remember what that is from memory, but if you don't, it's 2.58. But if we don't remember that, let's load a z table in here. Okay, I wanted a 99% confidence. Okay, so I'm going to find a z sub alpha over 2, which would be 0.005. Okay, so that would give me then 0.995 as my area. And this one is the closest one in our table to 0.995. So we'd have a 2.5 and then go up. It'd be 0.0. So 2.58 is the z-score. 2.58 is the z-score that goes with a 99% confidence level. Okay. Now we would use that. So I'm going to say z sub alpha over 2 would equal 2.58. That's when sigma is known and n is greater than or equal to 30. Okay. Here it says identify the t-score for 99% confidence level for n equals 1,001. So that means my degrees of freedom is going to be 1,000. And when we do that, and I think the table I have, not all tables are going to do this, but my table here, you get up to 40, it starts jumping by 5 for degrees of freedom. Up to 80, 90, 100 it jumps by or tens. This jumps by 400, and it gives me to 1,000. So if I have 1,001 as my sample size, then 1,000 my degrees of freedom. If we look at 99 percentile, it's 2.58. And if I go to infinity, it's 2.576. And you see here that when it says infinity, it's actually got a z in parentheses. And what that means to us is that as our sample size increases, and that's what I was trying to show you with the degrees of freedom here. If we show both these distributions, as our sample size increases, so does our degrees of freedom, and when that happens, we get these areas to be very, very close to one another. So let me see. Let's show this area here. Let's make it yellow, and let's do the other area. Let's see if we make that blue. All right, so when degrees of freedom are smaller, so that area, the blue area is 0.968, and the yellow area is 0.915. That's quite a bit of difference. That's a 5% difference. Okay, but as we increase our degrees of freedom, so our sample size is getting larger and larger and larger and larger, we start to see that this number here, which is the area under the t-distribution, starts to merge or migrate towards the area underneath the normal distribution. And that is no longer a huge discrepancy in regards to probability. And basically what our table is showing then is essentially when this gets to like 1,000, there's really no difference between the two. All right, and that's the conclusion. So what is the conclusion you make about the t-distribution as the sample size increases? As the sample size increases, the t-distribution starts to migrate into or resemble or turn into the z distribution or the normal distribution. Okay. I'm going to stop there with the introduction to the student t-distribution. Tomorrow's class, we will start getting into examples. Okay, so my hopes are we're going to wrap our brains around this concept. We can wrap our brains around this formula here. Very similar formula to what we've already done with the z distribution, normal distribution. And then I also want to make sure that we go back to the 8.1 and half section and make sure that we are comfortable with what I was mentioning with degrees of freedom. Okay, that's not in my OneNote, but that is in Schoology. Make sure you read that synopsis I gave you there and watch those videos.